Hey, this is Leach with Simpson Math, and today we are talking about the end behavior of polynomials. Now, before we get to the end behavior part, let's talk about what in the world a polynomial is. So let's consider this polynomial, 7x to the fifth plus 5x cubed minus 2x plus 1. Well, first let's just define the parts of a polynomial. So we have terms. This particular polynomial has 4 terms. It's a 4-term polynomial. Terms are separated by addition and subtraction symbols, and they're bound together by multiplication. So this is collectively a term. Now, specifically, we call this first term the leading term because it's like they're in a line and it's the one that's in front. It's the leading term. The coefficient, the number that is in front of the variable, is what we call the leading coefficient. So it is that's going to be an important number in a minute when we're dealing with our end behavior. So this term, the very first term, is the leading coefficient. Now, you can't just put any old term in front. You have to make sure that the leading term is the term with the biggest exponent. So if we look, we have these exponents 5, 3. Now, if you look at this negative 2x, I don't see an exponent, but there is an implied secret 1. And at the end here, I don't see a variable or an exponent on the 1, but there is an implied x to the 0 power. Remember, any non-zero raised to the 0 power is 1, so there's an implied x to the 0 here. So if you notice, our terms are written in what we call descending order. We have the fifth, and then the third power, and then the first, and then the 0th power. We write them what we call descending order, biggest to smallest. This biggest exponent is what we call the degree of the polynomial. We're going to be abbreviating the degree of the polynomial as just DOP. So this first term we call the leading term. It's the one with the degree of the largest exponent, and its coefficient we call the leading coefficient. So polynomials have certain rules. So let's take a look at these 4 examples. X to the 1/2, well, that is not an integer exponent. That's actually the square root of x, and that is not a polynomial. X to the -1. -1, that is an integer, but it does not fit the non-negative category. And this would actually be expressed as a rational function, 1 over x, and that is not a polynomial. X to the 3/4. Well, a 3/4 exponent would be the same thing as the 4th root of x cubed, or the 4th root of x, and then all of that cubed. This is not a polynomial. And then lastly, x to the -2. That -2 is again non-negative, and that would be 1 over x squared. If you look at our polynomial here, all of these are positive or 0 integers. That's why we say non-negative, because we do include 0. Also, polynomials are smooth and continuous. There are no corners, no cusps, no kinks. So you're not going to see it have a corner. So it means our absolute value function, that is not a polynomial. It's going to be nice and smooth like this. So the domain is going to go from -infinity to infinity, but also there can't be any jumps. So if I have a function like this that we might have seen when we graphed domain, and where we have this break or this jump, that is not a polynomial either. So it has to be smooth and continuous. You should be able to put your pencil down at like -infinity, if you could reach it, and go all the way to positive infinity without ever picking up your pencil. Let's take a look at these 6 polynomials and observe some similarities and differences. If you look at the degree of the polynomials for each of these 6 examples, I'm increasing by 1 each time so we can see what happens. And I also include the name of this particular type of polynomial that's based upon the degree. So when I have a degree of the polynomial that's 0, that's just a constant flat line. Notice there's an implied x to the 0 power after that 4, so the function f of x is 4 is just a flat line. If I have the function f of x is 2x minus 7, you've been graphing that since Algebra 1, and this is just our linear function, and its degree is 1 because we have that secret 1 right there. Then you should also be experts at graphing quadratics. So I could have asked you with transformations of functions to graph this, -5x squared, and that looks like our parabola, that upside down parabola. And it is a quadratic with a degree of the polynomial of 2. Well, you might be thinking to yourself, this cubic doesn't look like any cubic I'm familiar with. I like to think of ones that's just with that little wiggle in the middle. Where's the little wiggle? Well, when it's just x cubed and transformations of just that one shape, it is just that graph with a little bit of a wiggle. But it actually, cubics can be a little bit more involved, and we can have functions that turn like this, that have these multiple turns. When we're just looking at just the x cubed with that one little wiggle, it's when these turns are sort of kind of just on top of each other. And we'll talk more about that in a later lecture. All right, then we have quartics. That's when it's to the fourth power. I just said ... because I wasn't worrying about the other things. Because notice these different shapes are really just depending upon that leading term. So quartics have these 3 turns, and our 5th term polynomials are called quintics, and we have all these different turns that are possible. All right, the first thing I'm going to do is I'm going to draw a horizontal line between some of these functions. I want you to notice something about where I draw these lines. What is the most number of times that this horizontal line could touch or cross these particular functions? Well, with this linear function, no matter where I move this line, it's just going to touch once. With this quadratic, which didn't end up very horizontal, let me fix that. There we go. Now with this quadratic, if I move this horizontal line, it could either cross twice, or it could maybe touch and turn and just touch it once, or never. But the most number of times would be twice. Look at the cubic. I could cross 3 different times. I might just do once, but the most number of times is 3 times. Look at the quartic. The most number of times it could cross would be 4 different times. It could just do 2, it could be never, but the most is 4. And then hopefully you're seeing the pattern. With the quintic, with 5, it could touch across 5 times. It could just do it once. Could do it 3 times. It could touch and do some different things, but the maximum number of times that it could touch across is 5. So notice that relationship there. You should have noticed that the degree of the polynomial equals the maximum number of intercepts. And ultimately, we're going to be interested in not just any old intercepts of a horizontal line, but the intercepts of the x-axis. So again, the degree of the polynomial is the maximum number of x-intercepts. And also, just vocab term, we've talked about roots previously, but technically we're calling them complex roots. So the degree of the polynomial equals the number of complex roots. Remember, a root is the value of x that makes the y value, or just the value of the function, 0. Now, you might have noticed something about the turns. Let me highlight them. Well, the quadratic function turns around once right there. The cubic function can have 2 turns. The quartic can have up to 3 turns, and the quintic can have up to 4 turns. So we should be able to see that the maximum number of turns in a polynomial is 1 minus the degree of the polynomial. All right, now let's talk about the end behavior. We're going to do what's called the leading term test. If you look around the internet, you might see someone refer to this as the leading coefficient test. But it's more than just the coefficient, it's that whole term. So I call it the leading term test. So first, we do look at the leading coefficient, which we abbreviate as LC. And this helps us determine the rise or fall of the polynomial to the right. So if the leading coefficient is positive, then the polynomial is going to rise to the right. Now, here's a notation that we're going to talk about in a minute. But this says, as x approaches infinity, the function approaches infinity. So remember, x is our input, and the function is the output. So as the inputs or our x's go to infinity, then that means that also the outputs will go to infinity. Now, what if the leading coefficient was negative, meaning it's less than 0? Well, then the polynomial is going to fall to the right. So as x approaches infinity, as x gets bigger and bigger and bigger, our output, our y, is going to be getting smaller and smaller and smaller. That's why it falls to the right. The other part of the leading term test has to do with the degree of the polynomial. So second, we look at the degree of the polynomial to determine the rise and the fall of the polynomial to the left. So if the degree of the polynomial is even, then it has the same end behavior. If it's odd, then it has opposite end behavior. So let's take a look back at these 6 sketched graphs on the previous page to see our new end behavior rules applied. Notice only one of our polynomials has a negative leading coefficient. So as I go from the center towards the right, this function falls to the right. So as x gets bigger, the output's going to be getting smaller. And that really shouldn't surprise us because we know that if this value is negative, in terms of graphing, our a is negative, and so it will reflect over the x-axis. So this shouldn't be a shocking result. All the others, excluding the constant, which doesn't increase or decrease, all of them are rising to the right because they have a positive leading coefficient. Next, let's take a look at the even versus the odd. So the odd has opposite in behavior. So the degree of the polynomial is 1, 3, and 5. Notice all of these are falling to the left. So when one side is rising, the other side is falling. So if this would have been a negative x to the fifth, it could have been something like this, where it's just basically a reflection over the x-axis. Now over on the evens, notice they have the same in behavior. So if I'm falling on the right, I'm going to be falling on the left. With this quartic, I'm rising to the right, so I'm rising to the left. They have the same in behavior. All right, let's take a look at some examples. We have two examples that we're going to cover. Most of the new material is actually pretty quick. It's just about that in behavior, number of turns, number of roots, that business. I am going to be reviewing stuff that's going to be more important later in some future lectures, the finding the y-intercept and the x-intercepts. And you're going to have a little bit of practice with that as well on your homework. So let's take a look at determining if the function's a polynomial, and then if it is, we'll determine the in behavior, the number of roots, and expected turns. We'll sketch a graph, and that's really it for the new material. But then just for practice, we're going to find the y and x-intercepts. So first, let's take a look at this function. F of x is 4x cubed minus 16x squared minus 9x plus 36. So first, let's talk about the leading coefficient. Our leading coefficient is 4. I don't care about the 16, this 9, this 36. They don't determine the end behavior. The reason for that is as x gets bigger, this term is going to be winning. It's going to be beating out whatever is going to be happening here. Because if I plug in 1,000,000 and cube it, that is way bigger than just a measly million squared. So this term wins as x gets bigger and bigger. So this 4, the sign of this 4 is what drives whether we're going up or whether we're going down. So since this 4 is positive, it's bigger than 0, this function is going to rise to the right. Now, what's the degree of the polynomial? Well, the degree of the polynomial is 3, so that means that it's odd. So then it's going to have opposite in behavior. So the function will fall to the left. Additionally, from what we saw earlier, the degree of the polynomial is also the number of complex roots that we have. So we have 3 roots. That means that we're going to be expecting 3 x-intercepts. And you saw as I moved that line around on those sketches that we're not guaranteed to have 3 x-intercepts. We might just have 1 or sort of kind of 2 if it hits in a very specific spot. But we're just going to say that we're expecting 3 or we have a maximum of 3. And we're also expecting 2 turns. We know that we had cubics that don't even turn at all. We saw that with just the parent function x cubed. So, but we're expecting 2 turns, or that's the maximum number of turns. All right, so let's sketch our graph. And when we do, we get this. We know that's going to be rising to the right, falling to the left, and then we have 2 turns. All right, now just for practice, let's talk about finding the y-intercept and the x-intercept. So we are able to find y-intercepts whenever we plug in an x value of 0. So we evaluate the function at 0. So when I do f of 0, I'm going to plug 0 into my function. And notice what happens to everything but the 36. They just become 0. So if I add up all those zeros in 36, we just get 36. So when I plug in a 0, a 36 comes out. And so we have a point 0, 36. Do note that this 36 is our constant term. And you might think for a second, oh, is this one of those just weird coincidences? And actually think about it. That's not the case. This is always going to happen. Your y-intercept of a polynomial is going to equal just that constant term, because every value with an x in it, which is going to be all the others but the constant, are going to go to 0, and we add them all up, and we just have that constant term. All right, to find the x-intercept, we need to set the function equal to 0. So set the function equal to 0 and solve. So if I look at this 4-term polynomial, I think to myself, oh, okay. Well, it's 4 terms, so the only thing I know to do with 4 terms right now is to factor by grouping. So let's try that. So if you factor by grouping, I can group up the first 2 terms, and then the second 2 terms, and factor out a common GCF. And I do, and I can get a 4x squared out of the first 2, and then a minus 9 out of the second 2. Make sure we change that second sign. And then I notice that x minus 4 is the same in both of my terms, so I can factor out another x minus 4. And when I factor out that other x minus 4, I have x minus 4 times 4x squared minus 9. All right, so I've done a pretty good job factoring, but look what's there. This 4x squared minus 9, that's actually another thing I can factor. That is the difference of 2 squares. 4x squared and 9 are all perfect squares separated by a minus, so I can keep going. So I can factor that as a difference of 2 squares, and then I set each factor equal to 0, and I end up with x equaling 4, x equaling negative 3 halves, and then x equaling positive 3 halves. So then I have my x-intercepts, and I like to write them in order from least to greatest. Negative 3 halves comma 0, 3 halves comma 0, and 4 comma 0. Now, just a reminder, this business about the y-intercept and x-intercept, that's a little bit extra. It is going to be on your homework, but really I'm preparing you for what's to come. So the only thing that's super new that we got to worry about is this leading coefficient and the leading term test. So let's do one more example. All right, so g of x is 10x cubed minus 3x to the 4th plus 8x squared. All right, first, so I need to do my leading term test. First thing with that is the leading coefficient. So my leading coefficient is, what'd you say? Did you say 10? Or did you say negative 3? Yeah, I was being a little bit tricky here. You gotta make sure that when you look at your leading coefficient, that it's actually attached to the leading term. That's the term with the largest exponent. So I had to just do a little bit of rearranging here. Remember, addition is commutative. So I just pulled this entire thing. The negative belongs with that 3x to the 4th and put it in the front. It's a positive with that 10x cubed, so it's a positive 10x cubed. Make sure that your polynomial is in descending order before you start doing this. So now, what is our leading coefficient? Hopefully you said negative 3. So if it's a negative 3, is that positive or negative? Well, it's right there in the name. It's negative. It's less than 0. So what's it going to be doing to the right? Yes, it's going to be falling to the right. So it's going to be going down to the right. All right. Next, we need to look at the degree of the polynomial. So what's the degree of the polynomial? Hopefully you said 4. So if it's 4, is that even or odd? That's even. And so then if it's even, is that same or opposite in behavior? It's the same. So degree of the polynomial is 4. We have even in behavior. It's even. So therefore we have same in behavior. And it's going to fall to the left. And then again, 4 roots, because the degree of the polynomial is 4. And we're expecting 4 x-intercepts. And expecting 1 less than that 3 turns. All right, so the sketch, we're going to be falling to the right, falling to the left, but we're going to be expecting 4 turns, so it should look something like that. So our polynomial as a quick sketch should look like that. Now, if you're freaking out going, these are very weird sketches, our next lecture, we're going to be actually putting them on graph paper and dealing with our x and y intercepts and a few more points. So today's just making sure we understand in behavior. So let's get that practice in for where we're going when we're worrying about that graphing later. So let's find the y-intercept. So to do that, we plug in 0 into our function. And again, that's pretty easy because it's just our constant. But what's the constant term here? Well, the constant term is actually just 0. There's a sort of implied secret plus 0 at the end of our polynomial. So that constant is just 0. So we have a y-intercept of 0, 0. And also note, that's also an x-intercept, because that's when one of our y values is also 0. So let's find any other potential x-intercepts. All right, so now let's find our x-intercepts. We're going to set our function equal to 0, and then we need to factor. But before we factor, always make sure to check for easy factors like GCF. So I'm going to factor out a negative x squared. Remember, if that leading coefficient is negative and you got to factor, it's easier to go ahead and pull out that negative. So factor out that leading negative. Now we need to factor this trinomial. So I'm going to do the AC method. I'm going to do a times c. I get negative 24. And then the factor pair that works is 2 and negative 12. So I split that b up into 2 and negative 12. And then factor by grouping. And I get x times x, and I get x times 3x plus 2. And then negative 4 times 3x plus 2. And notice the 3x plus 2's match. They better, because this is factorable. And so I can factor that out. And it can't factor any further, so I can set my values equal to 0. And I end up with my 3 x-intercepts. Negative 2/3, 0, 0, 0, and 4, 0. Again, I like to write them in order from least to greatest. All right, so that's in Behavior of Polynomials. There's going to be 2 subsequent videos, one about just approaches notation. It's this notation that you saw earlier right here, just some more detail about that and how they can apply to non-polynomials. So make sure to check that out. That's on the homework. And also a quadratic formula review. That's additionally on the homework, because if you come across a polynomial that you can't factor, then you'll want to be able to use that. This is just a review of prerequisite knowledge, so make sure to check out that video so you can be prepared for the homework. All right, thanks, and see you in the next video.